Right, let's look at question 3 of common test 2, the mock common test. So data given, the model is proposed. The idea is we want to perhaps investigate whether this model is the right model to estimate, to represent actually a population of kangaroo in this national park. So how do we find this algebraically? K is 240 and so on. I would do like this. You might have your own approach. It's hard to say whether it's wrong or right if you use your approach, because as long as there's a valid reason for you to do so, I think we should accept that answer. Anyhow, this is how we do it. The P T is given as KEBT, and in the table, if you notice that when time is 0, population is 240. So when time is 0, this is 240, and this is KET 0. Of course, we know that e to power of 0 is 1. Therefore, we have what we need. K is 240. Let's make it nice. K is 240. It's shown. Just nice. Moving on. How do we show that B is 0.333? I'm going to cheat a little bit, because you see that the model is given. This is linearized. It means that when we learn a certain exponential function, what we get is a linear function. Well, that's a long story, but it is a linear function. So we start with the PT again. Now we know it's 240. We place and we take ln both sides. And again, the law of log would be applicable here. Apply that, and I'm gonna skip ahead. Why we getting this? And then this is 1. Let's keep it as ln 240, and I'm going to rearrange this a little bit. So you see this ln 240. If you check ln 240, its value is roughly 5.481 and so on. So if you compare this with this model, comparing, we discover then B is indeed 0.333. Now moving on to here, how using the proposed model. So we have this Y, we know now it's 240, E 0.333T. Right, cool. So how many kangaroos are in Mount William National Park on 1st of May? Now, first, some idea about time, duration, interval. So when time 0 is actually 1st of January 2009. It's first month, second month, third and fourth and fifth and so on. Now the first month would be like 1st of February 2009. Second month, 1st of March 2009. Third will be 1st of April Fool's Day. Of course, nothing foolish about this, but moving on. This is the 1st of May, Labor Day here, and this is how many months? Let's see, 1, 2, 3, 4. So 4. And from the table, if you go back and check the table, here's it. This is it. It's a table. So we know that actually we don't have to calculate this. When time is 4, the number, or I should use P here. Okay, the population is 909. This is directly from a table, right? Isn't it straightforward? And then predict the number of kangaroos on 1st January 2011. 1st January 2011, it means that time is what, 1st of Jan 2009, so with 2 years after, which means T is 24 months. And all you have to do, just calculate 24 and put this into calculations, you know, E 0.333. You'll be amazed, this is going to be a huge number. So it's going to be roughly equivalent to, let me check, 729.2 or 3, I think, but it doesn't matter because we'll just take 709,730, you know, the whole number. So that's our estimation. Okay, let's move on. Next one. So they ask us to find P prime for and interpret your answer. Anyway, let's just find P prime. So PT, again, I copy this here. E 0.333T. Oh, there's no negative here. And P prime is, so 240 times 0.333 E to the power of this one. If I simplify this, it should be 79.92. So when T is 4, that would be roughly 303. Okay. Now what does this number mean? Okay, so this is a rate of change of population respect to time. So we then know that the rate, and this is a positive value, so that implies that the rate of population is increasing, right? Increasing is going up because it's positive. So you see the rate, not just rate of change, but very specifically rate of increase of populations is 303 when time is exactly at 4 months. Alright. Lastly, a comment on the validity of this model. Now, intuitively, you probably realize this is the lousy model, not a very good model, because just after 2 years, you have what 700 over 1,000 kangaroos. It's crazy. We start off with 240. So this would not sustain. I mean, there's not enough food. They will be crowded. Unless kangaroos, they like to stay in flats, right? So this is totally unacceptable. But no, not probable. I'm trying to say. So we need to support our idea, our argument with some a bit mathematics. Look at this. PT is 240 E 0.333T. Now what I want to do is I try to say that, argue by saying that as T tends to infinity, P is this one 333T would definitely tend to infinity. So P would therefore tend to infinity, and this is crazy. Now even you can check, put in a number, say like after 4 years, 48, you have actually over 100 millions or more than that. So this model is not feasible because it doesn't take into account the resources and so on, and therefore not valid. Alright, so okay.